Greetings, parasite ecologists. You must be on the edge of your seat, because I dropped a bomb in the last video. The eusocial insects, like ants, use division of labor, splitting their colony up into workers, drones, and queens. And unbelievably, the trematodes do the same thing. They also have division of labor, splitting their colony up into reproductive Parthenidae and soldier Parthenidae. Here's what that looks like. The large reproductive Parthenidae are specialized to reproduce. They grow really large, they have very small pharynxes, just big enough to eat, and they focus on pumping out cercariae. In general, they're not very mobile. In contrast, the soldier or warrior Parthenidae have enormous pharynxes, and they're relatively small because they don't contain any cercariae. Instead, what they do is jet around the snail, looking for invaders, and when they find them, they eat them viciously. What invaders, you might ask? Well, remember that Parthenidae are reproducing asexually, so the initial Myricidium colonizing the snail is genetically identical to all the Parthenidae that arise from it. So once you've got an infection going on inside a snail, it's in your best interest to make sure that it's just you and your genetically identical siblings using that resource, because if another genotype of your same species comes in, or another trematode species comes in, you don't want to have to split your resources with that new invader. So these warrior Parthenidae patrol the snail and chow down on anything they recognize as not genetically identical to them. And in that way, they make sure that all of the resources are sequestered for the warrior Parthenidae and their genetically identical siblings. Just as you see among worker bees, these warrior Parthenidae never reproduce themselves. But of course, they're identically related to all the reproductive Parthenidae, so it doesn't super matter to them that they never got a chance to pass on their own genes because their genetically identical sibling is already doing it for them. So an incredible microcosm of drama is happening, hidden inside the snail's body. Now let's peek inside the Parthenidae to find that next larval stage of the parasite, the cercaria. Once they've spent enough time developing inside of their rhedia or sporocyst, these cercaria will be ready to embark on the next stage of their life cycle, taking all of their trematode hopes and dreams along for the ride. Once fully developed, the cercariae burst out of their Parthenidae, and they're emitted from the snail out into the water column, where they swim around using their tail, looking for a second intermediate host. For Euhaplorchus californiensis, that second intermediate host is usually a California killifish. Once it intersects with a killifish, the parasite penetrates the skin, gets inside, and settles down, forming a cyst. So the cercaria, let's say it finds itself on a killifish and it's like,
great, this is a wonderful host for me to be in.
Now it will settle down and form a cyst around itself, creating what we call a metacercaria. That metacercaria just hangs out in a kind of hibernation, a period of metabolic inactivity, waiting for the second intermediate host that it is inside of to be eaten by a definitive host. Now, this metacercaria wants to get into the intestine of a bird, right? That's how it completes its life cycle. And that is called trophic transmission, where the final or the definitive host ingests the metacercaria in or on its prey. And this trophic transmission step is so-called because it's happening from prey to predator. The predator is getting infected by eating an infected prey. Once the worm finds itself in the intestinal tract of the definitive host, that metacercaria feels the change in pH and it goes,
great, I'm in an intestine.
And it uninsists. It can become its adult form. Now it can sexually reproduce, and the cycle begins all over again. This trophic transmission stage is a really interesting one because the metacercaria, it can just hang out in its second intermediate host and wait for trophic transmission, or can try and make that trophic transmission likelier to happen. And that is what we often see. Parasite-increased trophic transmission is this phenomenon where the parasite just slightly tweaks its second intermediate host's behavior in order to make it likelier to wind up in the jaws of the definitive host, which, of course, is terrible for the second intermediate host, but pretty great for the parasite. It increases the parasite's fitness, and so there is a strong selective pressure on trematodes and many other trophically transmitted parasites to develop these kinds of behavior manipulations of their intermediate hosts. Euhaplorchus californiensis is great at this because there's something I didn't tell you. about what the metacercaria do in their killifish hosts. Of course, they find the killifish, penetrate it, and form a cyst, or a metacercaria, inside of its body. But there's one part of the body that they really love to insist in. You tend to find metacercaria of Euhaplorchus californiensis on the killifish's brain. This is what a killifish brain looks like when it's infested with these trematode metacercaria. You can see that there's like a bumpy texture to the brain. That's because it is covered with thousands of trematode metacercaria. There's a really good reason for that. When it insists on the brain of the fish, the parasite can cause its host to exhibit really weird behavior. Killifish are, in an estuary, they're just snack food. Lots of different birds would love to chow down on killifish. And a normal killifish is correspondingly really shy, retiring, careful about the way that it shows itself to the world because it knows that birds are always above it, just waiting for the opportunity to eat it. But infected killifish will do all kinds of weird things. They'll surface, they'll jerk around, they'll shimmer and contort. And these are behaviors that they wouldn't normally exhibit unless they were infected, because it is exactly what the parasite wants. This plot was created by a couple of parasite ecologists who went out into the salt marshes of California. They collected a bunch of killifish, and then they brought them into the lab and put each fish into a tank and counted up the number of times it exhibited conspicuous behaviors like surfacing or jerking in a set period of time. And then they killed each fish and counted the number of metacercaria on their brain. The intensity of infection is shown on the x-axis, and the number of conspicuous behaviors on the y. And what they saw is that the more metacercaria there were on the brains of these killifish, the more conspicuous behaviors they exhibited. But the scientists didn't stop there, because they also wanted to know, would those conspicuous behaviors make the killifish more likely to be eaten by their bird predators, which are also the definitive hosts of the parasite? So they collected fish from an uninfected marsh, a moderately infected marsh, and a heavily infected marsh. And they put each group of fish into separate floating cages in a single salt marsh where there were many, many predatory birds. Now, these cages were open on the top so that the birds could hunt inside of them, but they were closed on the sides so that the fish couldn't escape. The scientists counted the number of fish that they put into each cage, and then they came back later on after the birds had hunted, and they counted again to see how many fish had been eaten by birds. Here are their results. On the x-axis is treatment, low infection, medium, and high. And on the y is the proportion of fish that were eaten by birds. And what this plot shows us is that infected fish are between 10 and 30 times more likely to be consumed by birds than uninfected fish are. Think about the implications of this. Through parasite-increased trophic transmission, this parasite is basically feeding birds. It is making a bunch more fish biomass available that otherwise would be inaccessible to birds. Let me give you just one more example. This is a species of trematode called Riboroia ondatrae. Like Euhaplorchus californiensis, Riboroia ondatrae uses predatory birds as definitive hosts. The birds poop out eggs, which infect freshwater snails, and the snail first intermediate host produces cercariae, which go out into the water column in search of a second intermediate host, which, for this parasite species, needs to be an amphibian. But rather than forming a cyst on the brain of their second intermediate host, Riboroia ondatrae forms a cyst on the developing limb buds of tadpoles. By interrupting the development of that limb bud, they actually cause the tadpoles to grow extra limbs. And these deformed tadpoles wind up metamorphosing into deformed frogs. And as you can imagine, they are really, really terrible at escaping from bird predators, just as the parasite planned all along. These infected frogs might be grotesque to look at, but despite this is a totally normal and natural process. It's just an example of a parasite trying to live its parasitic life. Euhaplorchus californiensis and Riboroia ondatrae aren't the only parasites that do this. Tons of other trematodes do, tons of other kinds of parasites do as well. Parasite-increased trophic transmission is actually pretty common across the parasites, as we'll see as we continue swinging through the branches of the parasite tree of life. I'll see you in the next video.